Hello everyone and welcome back. Today we're going to talk about the divergence theorem, and before we get to the theorem itself, let's just remember what the divergence of a vector field is. So if we have a vector field with component functions p, q, r that are differentiable, we define the divergence of that vector field using either the notation div of f or this del operator dotted with f as the partial derivative of the first component with respect to x plus the partial derivative of the second component with respect to y, plus the partial derivative of the third component with respect to z. So divergence takes a vector field and gives you a scalar function. So we talked about the divergence of vector fields back when we discussed Green's theorem, but let's look at some more properties of the divergence. So if we have a conservative vector field, that means that our vector field is the gradient of some scalar function, some potential function, and we take the divergence of that gradient, then what we're really getting are the second order partial derivatives of that function with respect to the same variable twice. In other words, if I take the divergence of this gradient, I get the second derivative of f with respect to x twice, plus the second derivative of f with respect to y twice, plus the second derivative of f with respect to z twice. So I don't get any of the mixed partial derivatives in here. Now this is an important quantity. It's called the Laplacian, and it shows up in a lot of partial differential equations. It shows up in physics and engineering examples and many examples in science. And it's either denoted with this delta or with the del operator squared. Okay. Now let's see how we can relate the divergence and curl. So if we try to take the curl of a divergence, we can't. Because remember, the curl acts on a vector and gives you a vector. But the divergence acts on a vector and gives you a scalar. So if we take the divergence of a vector field, we get a scalar function, and taking the curl of a scalar function doesn't make sense at all. We have to take curls of vector fields. So we can't take the curl of a divergence, but we can take the divergence of a curl. So if p, q, and r have continuous second order partial derivatives, and we take the curl of our vector field, which again gives us a vector field, and then we take the divergence of that vector field, what we get is these are the components of the curl here, and we're taking the derivative of the first component with respect to x, of the second component with respect to y, of the third component with respect to z. That's what it means to take a divergence. And we get these 6 terms here, where each term is a mixed partial derivative of one of the component functions. And if you look at the 2 I have for r, this is just the same mixed partial, taking the derivatives in reverse order. The same thing for q, I have the same mixed partial, but taking the derivatives in the reverse order, and the same with p. So we know from Clairaut's theorem, if I have continuous partial derivatives, which I've assumed here, then it doesn't matter which order I take the derivatives in, I'll get the same mixed partial. So if I have continuous second order partial derivatives, this is just 0 by Clairaut's theorem, the scalar 0. Or you can think the 0 function. We have a result that says if I have a vector field whose component functions have continuous partial derivatives, and the divergence of that vector field is 0, then that vector field cannot be the curl of another vector field because of this result up here. So if you have a vector field whose divergence is 0, and those partial derivatives are continuous, then you can't possibly be the curl of something else. So those are some more properties of divergence. Now let's review the flux divergence form of Green's theorem. So when we talked about the other form of Green's theorem, we said that the flux across this closed curve, so it was a simple closed curve in the xy plane. So the flux of our vector field across this boundary, which we could write as a line integral of p dy minus q dx, where p and q are the components of my two-dimensional vector field, is equal to the double integral of the divergence inside this region. So the divergence for a two-dimensional vector field was just the partial derivative of p with respect to x plus the partial derivative of q with respect to y. So here we have flux across the boundary of a region is equal to the divergence inside the region. And this was for 2 dimensions. But now we want to extend this to 3 dimensions. When we extend it to 3 dimensions, we get the divergence theorem. And here it is. So the divergence theorem says, let E be a solid region bounded by a piecewise smooth surface S with outward pointing normal. Now I'm going to use the word solid region quite a bit, but I don't mean solid in the physical sense. I'm just using solid to mean that it's some self-contained three-dimensional region. So I'm not talking about any kind of material properties or anything like that. So I'm just going to use solid as shorthand for three-dimensional region with a boundary. So we have some solid region. S is the entire surface of that region, and we have an outward pointing normal. If we have a vector field that has continuous partial derivatives on an open region containing E, so again we need to have a little bit of wiggle room with the continuity of these partial derivatives. Not only do they have to be continuous on E itself and on S, you have to be able to go outside of E just a little bit, or otherwise strange things can happen. So as long as that's true, then the flux of the vector field across the surface of this solid is equal to the divergence inside the solid. So here I have a surface integral, and here I have a triple integral. Okay. Now S has to be a closed surface, meaning that it completely encloses this solid region. So there's a difference here between our surface for divergence theorem and our surface for Stokes' theorem. If you remember Stokes' theorem, I had to have a boundary curve for my surface in Stokes' theorem. But for the divergence theorem, there shouldn't be any boundary curve at all because it completely encloses some region in space. So the key difference here, if you think of a sphere is a closed surface. It encloses a ball. It's the surface of a ball. But if I were to look at a hemisphere, that has a boundary curve. It has a boundary curve that's a circle, so that's not a closed surface. So that's the key difference here. For the divergence theorem, we need a closed surface. For Stokes' theorem, we needed a surface that had a boundary curve. Okay? Now, what the divergence theorem is saying is exactly what Green's theorem was saying in the flux divergence case. It says the flux of F across the boundary, so across the surface, is equal to how things are expanding or compressing inside the region, inside the solid. Let's take a look at an example. Find the flux of this vector field arctangent of the natural log of the square root of y squared plus z to the fifth as a first component. The second component is y squared plus z to the negative secant of x to the negative third. And the third component is hyperbolic cosine of hyperbolic sine of cosine of xy plus 2, all of that minus z. So I want to find the flux of this vector field over the cube formed by the coordinate planes and the planes x equals 5, y equals 5, and z equals 5. All right, well this looks completely horrid. But the divergence theorem says we can either compute this surface integral or we can take the divergence and compute a triple integral. Now, if we computed the surface integral, we would need to actually set up 6 different surface integrals because the cube has 6 sides. Now, each of these sides is a square, so each individual surface, it would be easy to parameterize and find the normal vector because they're just squares. And 3 of them are coordinate planes, so zeros would be plugged in for those variables, so it wouldn't be too bad. But the rough part here would be these component functions. Right? These look absolutely horrible to deal with. But what happens if we take the divergence? If I take the divergence here, I'm going to take the partial derivative of this first component with respect to x. There are no x's, so that's just 0. I take the derivative of the second component with respect to y, I get 2y. I take the derivative of the third component with respect to z, I just get negative 1. So the divergence of this vector field is 0 plus 2y minus 1. And I'm going to integrate that over a cube. Well, cubes are easy to integrate over because I just have all of the variables going from 0 to 5. I don't have any functions in my bounds. So instead of doing this horrible flux integral, I'm just going to integrate 2y minus 1 over this cube using the divergence theorem. I don't need to worry about normals or anything like that because inside this solid I don't need to integrate the normal vector. I just integrate the divergence itself. And so I get this triple integral of 2y minus 1 where all of the variables are going from 0 to 5. And I can completely separate this integral. This 2y minus 1 is just a function of y. So then I can think of it being multiplied by 1 as a function of x and 1 as a function of z and just completely separate it. Or I have just integrating 1 with respect to z from 0 to 5, integrating 1 with respect to x from 0 to 5, and I'm integrating 2y minus 1 with respect to y. So this first and last integral just give me 5. The middle integral gives me y squared minus y, and when I plug in 5, I get 25 minus 5. It gives me an answer of 500. And that's the answer. And I'm finished, and I don't have to worry about parametrizing any of the surfaces of the cube or dealing with that awful looking vector field. Okay, let's end the video here. In the next video, we'll do another example of using the divergence theorem, and then we'll summarize all the important results that we've covered in Chapter 16.